Yeah, you already mentioned the data scientists. They are, of course, a group being addressed here. Data scientists want to be able to, let's say, analyze even huge amount of data, maybe coming from heterogeneous sources. GRAS is able to, let's say, to funnel this into one system, to do the data cleanup at the same time, as I already mentioned. It's very interoperable. So you're not limited to GRAS if you want to bring it into a different final visualization system, no problem with that.
Welcome to another episode of the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. My guest on the show today is Markus. He is the founder of a company called Mondialis and he is the project steering committee chairman of the GRAS GIS project. GRAS GIS is a free and open source geospatial software. It has a rich history, a lot of functionality, and it probably doesn't get the attention it deserves. Thank you so much, OSGeo, for helping make this podcast episode possible. I really appreciate your support. Welcome to the podcast, Markus. I'm really looking forward to this conversation. We've had a previous conversation around GRAS and it was really eye-opening, so I'm looking forward to hearing more about it and, of course, sharing that with the audience. I think just before we jump into GRAS GIS as a project and as a piece of software, I think it would be really useful and helpful for the audience if we just could get an understanding of your background. How did you get involved in GRAS and how did you get involved in geospatial in general?
Hello, Daniel. Thank you for the invitation to this podcast. Yeah, well, I'm involved in the GRAS GIS project already for a very long time. I started back in the early 90s as a student helper at the university, trying to explore this software. The idea was to understand if it is a reliable software to be used in teaching and in research. I was involved, as I said, as a student. Then I finished my studies. I moved into science, into academia, worked for 15 years in Italy, in Trento, in northern Italy, in a research foundation. And everywhere we use GRAS for infectious disease monitoring, for satellite data processing, and so on. And it's always very nice when you are able to co-develop the software you are using, to bring it forward, to see that it grows, that other people use it, and so on. And importantly, the software is not my invention. It has been there already for 15 years or so before I even knew about it. It's coming from the old days in the 80s, and since then it is existing.
Thank you very much for sharing some of your background with us. But I feel like we've perhaps jumped in a little bit deep here. Maybe we could back up a step here and explain what is GRAS. So this is a geospatial podcast. We've been talking about software. People will understand that this is some kind of GIS software, but perhaps you could put a few more words around what GRAS is.
Yes, of course. So the acronym stands for Geographic Resources Analysis Support System, a very long one, commonly called GRAS or GRAS GIS, which is an open source software. It exists, as I mentioned, already for 35 or more years, which is like outstanding because it is an open source software originally developed by the US Army. And since the, let's say, early 90s, developed in academia, and even later with the advent of internet communities, developed like in a global team. It's a software which does a lot of different things. It's a powerful raster vector and geospatial processing engine, means you can do all sorts of analysis there. Maybe we come to it a bit later. There are really plenty of applications existing. And you can consider it as a kind of toolbox, which comes with a tool for more or less most of the geospatial topics. Importantly, you can use it on a desktop or a workstation, a laptop, whatever you like a standalone application with a graphical user interface or like a standard GIS software. Additionally, it is also used as a backend in many projects, different projects. I mean, you can use it from QGIS, another well-known open source software tool. There under processing, you have the access to much of the GRAS functionality. You can use the R geostatistical software. There's a bridge to it, or you can even use it in the cloud. There is a new software, also a OSGeo community project called Actinia, which enables you to run GRAS analysis in the cloud. GRAS is a founding member of the Open Source Geospatial Foundation, OSGeo, which was established in 2006 and is, of course, an important part, a project of this software foundation, which also grew quite a bit. The software is developed, as I mentioned, in the internet, through the internet on GitHub. So we are using modern technology for the development, for the review of the changes, for releasing new versions and so on, packaging whatsoever. And I would say the 35 plus years show that a lot of fancy algorithms could be included. Optimization happens all over the time. If things happen in the geospatial world, the GRAS project seeks to pick this up, like new formats, new ideas, new algorithms. They are integrated, and it's a community project which is open to everybody, but it's also used in commercial settings, not only academia, also in business, where it is the backend for analysis.
Thank you very much for that. I just want to summarize a little bit here for the listeners. So we have this open source geospatial software, GIS software called GRAS. It's got a long history. It has a ton of functionality for raster and vector data. We can get to it from different places. I know that a lot of the functionality is integrated in QGIS, for example. You mentioned a couple of programming languages there, R, and I'm sure there's a connection or a bridge to Python as well, so we can access the functionality that way. There's a user interface as well. One thing I want to talk about in terms of GRAS, and this is from my personal experience with it, is that I found it a little bit confusing at the start. So when you open the user interface, if you're running it as a desktop application, there's something called a directory, a location, and a map set. Would you mind walking the audience through what these things are and why they're necessary?
Yeah, sure. We have, in the first place, like in any GIS, you have to store your data somewhere. We call this GRAS database. This is basically a folder or directory somewhere sitting on your disk or on your network drive, wherever it is, and you have to organize your data somehow. And most people probably think along the lines of projects. So this is my folder for project A, and this is folder project B, and so forth. We call this locations. This is a slang which comes from the initial days of GRAS development that was called locations, and we kept it like that. So you can probably say it's a synonym. Project and location is the same thing, where a folder, which is a folder or many folders where geospatial data are stored. There's one important thing about these locations. A location can usually relates to one geographic place or area of your interest. We could also define this place as large as the globe. So we have a global location. By the way, you can also use Mars data. So if you want to change the planet, no problem. You can do that. And within the location, the data are stored, as I mentioned. But importantly, in one location, you can have only one coordinate reference system. You may think this is a kind of limitation, but it's also the idea of keeping data clean, to avoid mixing. And those who are more deep into GIS data analysis know if you reproject data, there are all kinds of things to be considered, like precision, like resampling with raster data, which resampling method is the right one, and so on. You need to be a bit careful if you want to do it right. And so the decision was, and this was not touched so far, in one location we have one coordinate reference system as the main one. But if you come with data which arrive in a different coordinate reference system projection, then you can reproject that on the fly. As a summary, location is a kind of folder in which the data are stored, and then within that there's a so-called map set or many map sets to even organize better your data. So now you said when you start GRAS, you are presented with this startup screen where you have to say which location do you want to use and which map set. That is more or less the idea to show you the folder structure and ask you which one do you want to use. We are currently working on a different version. It will be likely GRAS 8.0. And there we are abandoning this welcome screen, and you just start GRASS as you start most of the other GIS. You are presented with the menu, and then you can do things with your data. So we are a bit inverting the order, but essentially the management will remain the same. There's one thing to know. GRASS data are coming in their own format. There's many existing formats out there, and GRASS amusingly is one of them because it exists already since the 80s, but it has never been standardized at international level to become a formal one like GeoTIFF or GeoPackage or shapefile. The GRASS format is similar to that, but it's just not really exposed like that. Why do we keep that? Because for more or less every format has to come with some limitations, and the GRASS format is a better representation in many regards, which, let's say, help you to minimize the loss when you store your data.
Okay, so if I understand this correctly, we have these location and map sets, and we can understand these as projects. The location is limited to one projection, but everything is projected on the fly. And so when I import data into a location, I have the option of reprojecting that into that location, and then it exists there. And I'm assuming now I can take any file I want, so a shapefile, for example, import it into this location, make sure the projection is correct in regards to that location, and it'll be converted into this GRASS format. What advantages do I get with this GRASS format? You mentioned something about the size and storing data effectively. But I also know from a previous conversation that there's something around the vector topology engine of GRASS. Could you talk to that, please?
Yeah, of course. So the vector topology engine is something very interesting. There have been more topological GIS out there in the past. This was a kind of, let's say, abandoned when it came to simple features, the simple features idea, which of course comes also with some advantages. But we should probably explain first what topology really means for vector data. So imagine two adjacent parcels. It could be some land use parcels, agricultural fields, or something like that, that are next to each other and they share one border. In simple features format, you would digitize two lines there, two borders between the fields. So it means each parcel comes with a complete border. In a topological model, this theoretically shared border is also really physically shared because there's only a single line. It means the common border between the two adjacent fields is one line and not two lines. Sounds simple, but it is less so because when you digitize, generate data, often in a non-topological model, the lines do not really match. You have to be very precise when you set your lines and your vector points, the vertices, one on the other, and so on. But unfortunately, this doesn't always happen. And we have plenty of data out there. You will also find them on official sites, maybe administrative boundaries, which are not digitized properly, where you have topological errors. There may be like small overlaps or slivers, that is small holes between these shared lines. This is a big problem, and especially with political relevant data or cadastral data, it's not a good idea to have those issues. So here the topological model comes into place. You have only one line, and through that you cannot have errors here. This is quite interesting. And the big advantage is when you import data into GRASS, vector data in this case, which have topological errors like overlaps and so forth, the engine will tell you, the GRASS engine will tell you, look, here's an error, please fix it. Or you can also automatically fix that with some snapping engine, which is included, and removal of duplicate lines and so forth. There are plenty of tools included. Thanks to that, you can clean up your data while importing them. Yeah, GRASS does a bit more than that. The topological data are important especially for areas. You have also the possibility to store 3D data, means vector lines which are inclined, which is relevant for all kinds of questions. And in the format, it's planned but not yet implemented. There are also 3D corpus there, which you could also store with topology. We can do that already, but it's not yet following the topological paradigm.
So a couple of questions spring to mind here. And the first one being, we're talking about the lines, so that the actual geometries here that are being corrected as they come into the GRASS engine, or you have the option of automatically correcting them. Does that also mean that I am building a data model in the background? So I'm calculating these topological attributes for each feature that's coming in, so they know each other's neighbors, for example?
That is right. For example, in a simple feature model, you don't really know what your neighbor is because you are a self-contained polygon, an area, a closed line, and you do not know anything about your neighbors. Is there a neighbor at all? Who is the neighbor? And so forth. No idea. In a topological model with the shared boundary, or yes, the common border between the two adjacent polygons, you know that because when we are importing the data, we look at it like a ring and we follow the ring unless we reach the starting point, and we know what is left and right. GRASS also stores a centroid inside the ring, and to form an area, we have a closed ring with a centroid inside. And of course, in the model itself, this is also important for attaching the attributes. So the attributes attached to that, the attribute table, the entries there. You can even attach multiple attribute tables if you have the need. And through that, you know everything also about maybe the side length, which is shared, and other information which are related to geometry.
So that this must have some sort of performance implications later on, because all this, I'm assuming anyway, is immediately available to me. It's calculated on input, so it's not something I need to generate if I want to do an analysis. Is that correct?
That is correct. It is generated during import, or if you digitize data inside, or you vectorize raster data, or do any other data creation task within GRASS, then it is immediately generated in the topological format.
What happens on export? So I bring my data in, let's say it's a shapefile again, I can clean it in this way, I can generate this topological model of it, and I'm assuming it's maintained when I'm doing my edits. Can I export it out to anything, or is it stuck in that format now?
It's definitely not stuck. We have export functionality there, and we rely on GDAL OGR for our, let's say, interfacing with the external world for raster and vector data. So in this case, OGR does the job to translate the topological model back into simple features. And through that, we can write out in more or less any format you can imagine, because OGR supports really a lot of them. Shapefile, GeoPackage, whatever you can imagine.
Earlier in the conversation, you talked a little bit about this GRASS data model. So we've talked about the GRASS data model for vector data. Is there something similar for raster data? Is there something that's calculated on import that's immediately available to me when I'm using raster data?
Yeah, with raster data, it's probably a little bit easier because in the end, we import a kind of grid or a matrix, which comes like in a GeoTIFF format or HDF or whatever it is. GRASS has its own raster engine, again, like with the vector engine, with the advantage that limitations like we have in GeoTIFF, that you cannot attach color tables to floating point maps and so on, is not there. Such limitations we do not have. We have a 2D raster engine there. We have also, interestingly, a multi-layer engine, so you can stack imagery like it happens with multi-band aerial or satellite imagery. But you can also, what is quite interesting, stack time series. So when you have time series, like we achieve nowadays with the satellite data, the operational one like Landsat, Sentinel, and so on, you can put them into a time series, and you can do all the computation on top of that. For example, if you look at temperature data, this could also come origin from climatic stations and so on. If you have a stack of raster maps and each of it is maybe the daily temperature in each pixel, then you can easily compute aggregates like what is the average weekly temperature or the minimum monthly or annual or decadal and so on. You can easily, from this bunch of input maps, generate aggregated output and, of course, do much more complex things than I just mentioned. Finally, we have a voxel engine that is raster 3D. That means we can store volumetric pixels, X, Y, Z, which is quite nice when you want to store soil profiles or atmospheric profiles or even medical scans. So imagine we are not limited to environmental data. We can also do import of maybe brain scans and then reconstruct a 3D volumetric model and visualize them.
In terms of the functions available in GRASS, does it matter? Like, are there specific functions for 2D or 3D, or do they just work on whatever they're pointed at?
Well, there are specific functions for sure. So we have really huge application set related to raster and vector 2D data. We have more limited because it's more complex, but also with maybe less need of functionality sets for volumetric raster and 3D vector data, and then additionally for time series. So maybe coming a bit to the set of applications, some examples. Imagine the solar radiation. We have a lot of dedicated tools in GRASS. As an example, solar radiation, we can compute the instant influx of energy on the surface. So imagine you have an elevation model, then you can compute over time how much energy will reach it. We can even do a normalization or a correction for clouds if you have cloud cover data available. But if you have a surface model which also includes the houses, then you can take care of that, and the inclination of roofs, for example, would be considered. So this is not a pure 3D application, but it's we call it 2.5D. It's a surface, but a surface with which describes also houses and other objects which are on the Earth's surface, and this can be used as well. Same thing applies when you do hydrological modeling, for example, flood modeling. Then you may also include buildings here, and these buildings will be considered when you do your surface flow and so forth. In the 3D world, last example, we have groundwater flow. We can do groundwater modeling. Here it's also interesting to look at the true 3D passage, and here the 3D raster engine comes into place.
I realize now that we've been talking about flat files, so importing things into GRASS and doing our work from there. Well, what does the GRASS ecosystem look like? Can I connect this to a Postgres database, for example? Can I use web services in GRASS?
Yes, you can. So the import of data is only half of the truth, let's say. If you have huge amounts of data, especially with raster data, it can nowadays quickly accumulate. You have the alternative, rather than importing it, to avoid duplication of disk space consumption. You can also register those data. That means you tell GRASS, look, here is the GeoTIFF file. I use GeoTIFF as an example. Here's the GeoTIFF file. Please use it. And the registration happens like a link. And GRASS considers this being a true raster map being imported, but it is not. It is just sitting over there, and there's the link. The speed penalty is really low, so you do not really realize that unless the file is remotely stored and you have to retrieve everything over network. But nowadays, even with cloud-optimized GeoTIFF and so on, we are seeing a lot of improvement here. What else do we have? Web services. So OGC web services are also supported. We have the possibility to read data from WMS, from WFS. So WMS for raster data, WFS for vector data, and web coverage service as well. And this gives you the possibility either to show such data in the display. So if you want to have a backdrop map, for example, but you can also truly save them in GRASS itself. So in case you, for analytical reasons, want to retrieve those data into your own database from the remote service, OGC service, then you can do so. And you ask about PostGIS. We can read and write to PostGIS. That is no problem. And also here, OGR is the interface eventually to make this happen, to translate between the topological engine of GRASS GIS and the usually non-topological engines out there or databases out there.
While we're talking about the ecosystem, now's probably a really good time to sort of talk in a little bit more detail about the programming interfaces to Grass. So earlier on you mentioned R, and I'm not sure if you mentioned Python, but I could imagine Python is one of them. Is there any other ways of getting at Grass functionality?
I didn't mention Python yet, but I must underline that probably nowadays 1/3 of Grass is written in Python. So Python is a key part of the system. We have several interfaces available. That means that, well, you can write your Python script if you want so, and you say import the Grass library, and then you have the functionality available. There's one on the pip server, there's one library called Grass Session, which is very handy. You just use that, and from there you can do straight away the usage of the Grass functionality, even without personally having started Grass. So you can use it as a backend there. If you want to develop additional functionality or combine existing tools, then you can write up your Grass script. There's one thing in Python, you can also do this in Shell. You can write in C, you can write in C++. There are also people who have used it in Octave or even PHP. So there are basically no limitations. One thing which I would like to mention, which is really, really specific, special, and very, very handy, is the parser. We have an included parser. What does a parser do? If a user comes and says, please execute this functionality, and by the way, use that input map, then we need something which is doing the communication. And let's say on command line, you enter a command into the terminal, can be on any operating system. You enter the command, and then the system has to read this. And this is done by a so-called parser. And Grass comes with its own powerful parser, which is specific to Grass, and it's able to understand parameters, distinguish flags. It doesn't mind if you mix the order. It can tell you, look, this is a parameter you have to specify, it's mandatory, or it can put default values where it is not needed, but you, let's say, usually go with one default value. And all this is done by this parser. This parser you can include in your scripts, whatever language it is. And from there, it can do a lot of stuff besides just understanding what the user wants, because it can generate also output. It can generate the description of the script you have just, a machine-readable description of what you have just programmed in XML, which can be then used elsewhere in other software or in WPS style. It can also, if you are lazy like me and you want to do something similar to what is already there and you do not want to write it all yourself, you just call an existing script with a parameter, and it will output this script in shell style or in Python style. And then you can just copy paste from there and continue to extend it to your functionality. And also the Grass user interface, it partially exists, but a lot of it is just generated on the fly. So all the buttons are generated also thanks to this parser with related button generate library, let's call it. But the description, how the button should look like and where they should be, is also done inside the parser. And the last example is that we can write out JSON. I mentioned in the beginning that we have support for, or let's say, available software which is called Actinia. You find it also on GitHub. The process chains, if you want to do process chains, generate process chains and use them in the cloud, you do not have to write everything yourself, but you can just tell the parser, today no Python, but please generate JSON style, and then it will output your scripts, which you probably wrote in Shell or in Python. It will output in JSON, and then you can drop it to the cloud.
I just want to make sure that I'm clear on this. And again, from previous experience with Grass, I know that there's a user interface, so I can push buttons and I can use the GUI to select and build up programs, execute functions, that kind of thing. And I know that there is almost like a command line built into Grass. Are we talking about the Grass command line here, where I can enter those scripts, or I can see the function that I've executed as scripts in that command line, and then say to the command line, hey, command line, give me this in Python, give me this in JSON, export this as something else? Is that what we're talking about here?
Yes, that's exactly right. So imagine you are using GRASS for the first time. You start it up with a demo data set, which you can download. There's a button for it in the welcome screen. You fetch the demo data set and you start GRASS. And then you go and say, okay, I want to see some map, like a road map, elevation model, whatever is there. So you click in the menu on the button to display a map. You pick the map and look at it. And this dialog, which asks you which map do you want to see, it has a copy button. And this copy button is showing you the command line, because in the end, the graphical user interface is internally also using the command line. It's just not shown to the user in a clear way. If you want so, you can see it, but it's, let's say, in the first place, it's kind of hidden. And then you could also copy over this command and put it into the terminal and run it there, and it would do exactly the same thing. So this is a so-called shell command. But if you then say you want to see it in Python style, then it will write out the style, let's say this command in Python, and you could copy it over to a Python script. Same thing with the JSON, same thing with XML, HTML, and so on. We also have a graphical modeler included in the user interface, where you could graphically combine commands and create your workflow. Let's say import data, do something with those data, and generate a report and store the report as a plot or a CSV file. This you see graphically, you can execute it and you see the results. But there's also an export to Python button there. And so you would be able to write out your first ever Python script like that. And this could then be run again as a standalone command.
So I think by now the listeners will understand that the GRASS is an open source piece of software. We can get to it from a lot of different programming languages. It has a ton of functionality. It does interesting things with the vector topology when we import it. It has a really, really good understanding of how data should be stored, and we can import and export a variety of different formats. I know from a previous conversation that it's got a very small memory footprint. It's a very fast when it executes. But one thing we haven't talked about so far in the conversation, which I think is becoming increasingly important for data scientists, is visualization of data. Is there an opportunity here to visualize data in GRASS?
Yes, definitely. We call it GRASS Monitor. So it's a graphical output interface like in any GIS, with the usual buttons and legend, map, styling, and so forth. You can also, if you, let's say, all the display part is like in any GIS. So you can display your data. There's a 3D viewer. You can also view your volumetric data there, and so on. If you digitize with the digitizer, then you have the possibility to check on the fly. It will show you if your data are topologically correct or not. With colors, red is not correct, green is correct. And you can query data, you can query plot time series, you can do basically all kinds of plotting. If you say, well, that's nice, but I prefer to view it elsewhere, then you have the possibility to export to ParaView. That's also a very powerful open source visualization tool. You can also use, as I mentioned, interface to R. You can interface to QGIS. There's the possibility to run it in Jupyter Notebook. So if you prefer Jupyter Notebooks, you can connect to that as well. And probably and all the kind of plotting tools, Matplotlib, Octave, and so on, there are plenty of them. They can also be connected to. So I would say you have the possibility to either do visualization right away in GRASS. And by the way, this is quite interesting. It is highly optimized. As an example, earlier this year, the NASA DEM, the reprocessing of the SRTM elevation model has been done. It is like, I don't remember, 250 gigabyte of data. If you import this into GRASS, this takes a little bit of time, naturally. It depends on the speed of your hardware as well. But if you say, okay, now I want to see the entire map, you can do so. It takes not much time, some seconds, I would say, and then you see the entire globe in the GRASS display. Why does this happen so quickly when it comes to hundreds of gigabytes of data? Because GRASS has an on-the-fly reduction tool. So let's say what is known as kind of lazy computation from other systems. you can reduce the resolution for the follow-up computation. And then, let's say, the huge data set is read as reduced resolution. The advantage is if you want to quickly try something on a huge data set, you can do so, and you do not have to wait forever. And then when you are sure that everything is in order and you will get the results you are expecting, then you set it back to the original dataset resolution and you retrieve the result. Similarly, for the display, because that was the topic, it is reduced on the fly. If you have a monitor with, of course, a limited amount of pixels on the monitor, there's no point in displaying 30-meter pixels of a global map because you won't see the difference. So GRASS does the reduction on the fly also for the display here, and that's why it is very fast in this regard.
Markus, you've given me and the listeners a lot to think about here, so I've really enjoyed the conversation up until now. I just have a few final questions for you. And the first one is that I think there's a lot of amazing open source software out there. There's a lot of amazing geospatial software out there in general. Who is GRASS addressing? Because we have the opportunity to do analytical work in other pieces of software. We have visualization packages already. If you had to sort of point at a group of people perhaps, or a particular use case and say this is made for GRASS, who would that be?
Yeah, you already mentioned the data scientists. They are, of course, a group being addressed here. Data scientists want to be able to, let's say, analyze even huge amount of data, maybe coming from heterogeneous sources. GRASS is able to, let's say, to funnel this into one system, to do the data cleanup at the same time, as I already mentioned. It's very interoperable, so you're not limited to GRASS. If you want to bring it into a different final visualization system, no problem with that. But I would say GRASS is addressing those who are in the need of doing complex, even simple geospatial processing of whatever format, of whatever data model, raster, vector, 2D, 3D, time series, and so on. And this is for sure not limited to academia, but it is also something which is supporting business models in all kinds of businesses where it comes to data extraction and, let's say, provision of conclusions or analysis on top of large amounts of data. And as we know, amounts of data are really, really increasing in this time. We are luckily having access to many new sources of open data. Open data, I would really like to mention here. This is a policy which is really important and bringing forward humankind, in my view, because especially data from public authorities should be available. But then the data are there. You have maybe LiDAR point clouds, and then what? And here we offer huge range of tools, and those tools are also at a high level of abstraction. That means you have topical applications there, fire simulation, solar energy, I already mentioned, hydrology, geology, and so on. So you do not have to reinvent the wheel, but you can just go there and use rock-solid tools which have been tested in many environments and optimized for speed.
And my final question here is, well, what do you think GRASS is going to look like in 5 years' time, or just generally going forward? Is there any particular direction you would like to see GRASS and the GRASS community head in?
Yeah, well, for sure, we can see that the open source approach, which I'm following already for 25 plus years, has developed from an academic niche, probably also back then due to the lack of globally accessible internet, to mainstream. So we no longer need to discuss if open source is good or relevant or such. It is. And GRASS is, of course, well settled there. I believe that in future, a plethora of open data sets will become available, and they require a new view on analysis. Having data is one thing, but being able to draw conclusions from data is another one. And here I see GRASS in a very good shape, because due to its modular architecture and flexibility, we can use it as a backend. in many regards, but we also continue to, let's say, develop the graphical user interface or other interfaces in a way that it is accessible to many. And I'm also pretty sure that more and more people, as it already happened, see the spatial component of many global problems and hence ask for software which is able to deal with that. And like this, we will continue the development and bring it forward so that such problems can be addressed in a way.
Thank you very much, Markus. I really appreciate your time, and I have loved listening to your insights and learning more about GRASS software. Where can the listeners go if they have questions, if they want to learn more, if they want to reach out to you personally?
So the first place is, of course, the GRASS website, grass.osgeo.org. Just relaunched this year, looking beautiful now. There you find all kinds of information. You see where you can start learning. You find the software itself. You find tools and information how to develop the software if you want to start. Then we have the mailing list, which you also find referenced there. It is running on the OSGeo domain. And the mailing lists are very friendly. So just post your questions. There is no bad questions. We are just happy to help, and they are, let's say, ordered in user list and developer list, but it's not a very strict separation. And well, you can of course reach out to me, netela@mondiales.de or netela@osgeo.org, and I'm happy to support you as much as needed, and of course help you also to navigate in the huge open source GIS community.
Thanks again, Markus. I've really enjoyed the conversation.
Thank you very much.
So Markus mentioned a lot of interesting resources during the episode here. I will put links to those in the show notes in your podcast application. You'll also be able to find it on our website, mapscaping.com. I really hope that you'll take the time to check out the GRASS GIS project. It really does offer a ton of functionality. It's free, it's open source, so you can just download it and start playing around, start learning. And that's it for another episode of the Mapscaping podcast. My name is Daniel, and it's been a pleasure being your host again this week. You are more than welcome to reach out to me on social media, or you can go to our website, mapscaping.com. And yeah, I would love to hear your suggestions, feedback, comments, that kind of thing. It really helps me shape the direction of the podcast. It helps me make it better for you. So any and all input is greatly appreciated. I would really love to hear from you. Okay, that's it from me. We'll talk again next week. Bye.